Hello everyone. So today we will be starting week 4 of the problem solving session for NPTEL. So today we will be doing what is taught in week 4 of NPTEL Communication Networks course, and what was taught is computer queuing theory. So today we will first briefly discuss what is queuing theory, and after we have done so we will attend to the problems, the assignment problems. We will try to solve them together. So this will be a problem solving session of about 2 hours. So first we will go to the basics of queuing theory. So let me share my screen. So we will start with queuing theory. So what is queuing theory? Queuing theory is that queuing theory is basically the science of the studying the arrival and service of information packets in communication network. So in a communication network, what happens is the packets are sent, and then those packets are received at the receiver, and in the intermediate stage there are multiple switches through which the packet runs. So these packets often come at a much faster rate than they can be processed. Say 10 packets can be processed at a time, but you are getting 20 packets. So you are getting 20 packets. So at a time only 10 packets can be processed. So if you only process the 10 packets while 20 packets have arrived, then you will lose the remaining 10 packets. So you will lose the uh, remaining 10 packets. So to prevent that, what happens is the 10 packets that are remaining, they will be sent to a different path, and through that they will be sent to a different path, and through that they will be so they will be stored in a buffer, and then after the first 10 packets have been serviced, then in the next slot the next 10 packets will be serviced. So these in this way, say 30 packets are coming. So what will happen is that mm, So here we have the basic definitions of queuing theory. So queuing system is model processes in which customers arrive, wait for their turn for service, and then when the packets are serviced, they leave. So basically, in a switch, the packets are coming, and when the packets are coming, they are getting serviced one by one. But if 10 packets are coming, then when one packet is getting serviced, the rest 8 packets, they have to wait in the buffer. So to do a statistical analysis of this waiting, and this waiting is called queuing theory. So there are multiple examples of queues. So supermarket checkout stand or ticket booths. Okay. So what are the five components of a queuing system? So the components of a queuing system are the inter-arrival time, service time, number of servers, queuing discipline, and size of queue. So these are the five ways in which components in which the total description of a queue is imbibed. So the first thing is the inter-arrival time probability density function. This is basically the PDF that gives at what rate are the packets come. So inter-arrival time probability distribution gives like, will in the next 10 minutes 10 packets come, or will in the next 10 minutes 50 packets come. That will depend on the inter-arrival time probability density function. Next is service time PDF. What is the time taken by the system to serve the individual packets. That is the service time that is given by the service time probability density function. Then there is the number of servers. So the number of servers is basically the number of like number of places in which the packets get processed. So if there are 10 servers, so 10 packets can get processed at a time. But if there is only one server, then only one packet can get processed at a time. Next is queuing discipline. Queuing discipline means the principle how the queue is managed, in what algorithm the queue is managed. That is called the queuing discipline. So this can be the first and foremost most common method of queuing discipline is first in first out. So the packets are sent and then they come at the server, and then they are made to wait in a queue, and the packet which came first will always get served first and hence will leave first. So first in first out. So this is one of the queuing disciplines. So there can be other queuing disciplines like, so one one common example of queuing discipline is first in first out, FIFO. Then it can be that all packets are coming and the last one to come will be served first. So it is like LIFO. So usually the most fair one is FIFO, but there can be other disciplines of queue. And last is the last parameter of importance is the size of queue. So how many packets are waiting? So this is self-explanatory. How many packets are waiting? Achha. Okay. So the fundamental assumption of the queuing theory that we will be doing in our class for network communication networks, the fundamental assumption is that an infinite number of customers will come. So the thing is, if a queue becomes long, then a lot of people will avoid that queue. So if you see in a ticket counter that there are like, you go to a place there where there is a ticket counter in a fair or in some mela or something. So you go to a counter and you see a lot of people are waiting in the queue. So you will not come. So even though you decided to come, by seeing the queue size, you change your mind. So this So even if a large number of customers come, but in a communication network queue, even if a large number of customers come, with in this case, customers are basically packets. So if a large number of packets come, then also another packet can come. So the large number of packet does not deter the next packet to come. So in real life, that does not happen. We usually get deterred by a large queue. So if we see a large queue, we say that it's not worth it to join that queue, and we avoid that. But in communication, that does not happen. So an infinite number of customers will keep coming. This is the fundamental assumption that we take. So this assumption is based. This assumption is bad in cases. So then, but in some cases, this assumption might be bad, like if there are a finite number of customers and all. but for our case this assumption is holds true. So next is inter-arrival time. So inter-arrival time is basically the time between the arrival of two packets. So one packet comes, then 10 minutes you wait, then the next packet comes. That is the inter-arrival. So list so you get the record the inter-arrival times. So the time between first and second packet, the time between second and third packet, the time between third and fourth packet, and you plot a histogram of that. Okay, so you group the inter-arrival times in bands. So that is called class. So 0 to 5, 5 to 10, 10 to 15, you do classes of this inter-arrival time, and then you plot the histogram. That histogram gives us the probability density function or PDF of the inter-arrival time. Next is service time. So what is service time? Service time is basically the time that the packet spends in the queue. So the packet says in the server. Sorry, the packet spent is in the server. So if you have one server, then that server will take, of course, one packet at a time. And how much time it will take, that can be random. So not all packets will take the exact same time, because they have different requirements, different services to process. So instead of fixing a fixed service time for all packets, what we do is we take a random analysis or a PDF, probability density function, for the packets also. Next is the number of servers. So number of servers means basically the number of packets that can be served simultaneously. And queuing discipline. So so queuing discipline is order of customer processing. So usually it is first come first serve, but in cases like hospital emergency room, in that case it is not first come first serve, but by the magnitude of sickness. So if you come for a checkup because you have fever, you come to emergency for a checkup because you have fever, you will be attended to. But if someone comes who has met with a road accident, of course they will be served first, because they might die if they do not get immediate service, which is not the case for you. So that's why strict first in first out is not maintained here in hospital emergency rooms. Similarly, in communication network, some packets are deemed more critical than others, then they might get a priority. So that is called a priority queue. So hospital emergency room is a priority queue. You are assigned a priority number, and you are served if and only if no one from a higher priority is waiting. So what is the definition of priority queue? That you will be served only if and only if no one from with a higher priority than you is waiting in the queue. If someone arrives who has a higher priority than you, then your service will be stopped, and the higher priority person will be put in the front of the line. So this is called a priority queuing. So that is another kind of priority queuing discipline. So in our case, first for analysis, mostly we will be taking the WEEK queue, the first in first come queue, because we have to do a random analysis of probability distributions, and first in first come is a random process, so you don't know which one will come first. But priority disturbs this randomness, so we usually don't study the priority queues. So finite length queues is another queue, a type of queuing discipline, where you will be put in the queue if and only if you will be within the queue size, within the queue length. So if 500 customers can wait at a queue and you are the 501st customer, you will not be admitted. So this is another. So in the so here in our communication network, what we do is we take single server systems. We have infinite buffer, means because we have infinite customers, so we will have infinite buffer, infinite packets. Since we have infinite packets, so we will have infinite buffer, because if one packet comes, it will have to get served, then the next packet comes, it will have to get served. So when that happens, at the same time, if the arrival rate is high, a lot of packets might come which might not get served. So since there are infinite customers, to handle them we need an infinite buffer, which is not practical, but for our assumption we will take for our analysis. analysis. So single server, next we assume that the server is a single server system. That is, one packet is getting served at a time. So one packet served at a time. One packet served at a time. And first come first serve. So here we have ABM notation. We follow the ABM notation for denoting a queue, where A is the type of PDF followed by the inter-arrival time. B is the type of PDF followed by the service time. So say this can be Markovian. This can again be Markovian. So MM. This can be again Markovian. So MM. And number of servers. This is usually 1. This constitutes MM1. So here A, B are chosen. So like this. So if if A is Markovian, that is inter-arrival time is Markovian, then the PDF it exactly follows is exponential. And if it is not following, the inter-arrival time is not following any randomness, and nor is not having any randomness, it is deterministic, then it is D. And if it is not Markovian or deterministic, then it is denoted by G. So MM1 is a known system. So MM1 system, now for an MM1 system where the inter-arrival time and service time are both Markovian, what is said is that the probability of exactly n customers arriving during an interval of length t is given by the Poisson law. So you have probably heard of Poisson process. So in Poisson process, what happens is the Poisson distribution governs the probability of how many customers arriving during an interval of length t. So for any arbitrary time length, how many customers will arrive will be given by the Poisson distribution. So the arrival is given by the Poisson distribution. So here the arrival time, here the arrival distribution, this is called the arrival distribution. Now if this is the arrival distribution, then so what does this denote? That this denotes that n packets will arrive in t time. N packets will arrive in t time. So P and T is given by lambda t whole to the power n by n factorial e to the power minus lambda t. So lambda t whole to the power n by n factorial into e to the power minus lambda t, where lambda, important, lambda is the arrival rate. So the only parameter here is lambda. So the probability that n packets will arrive in t time is lambda t to the power n by n factorial e to the power minus lambda t. So lambda is called the rate parameter, that is the event per unit interval, that is arrival per unit time. Arrival per unit time is called the rate parameter or arrival rate. Arrival per unit time, arrival rate. Lambda is equal to, so in 1 second how many packets arrive on an average. So arrival per unit time. So if the inter-arrival rate is 10 customers per minute and the number of customers is 100. So how many minutes will it take? 10 minutes for all the customers to arrive. So like that. Now, if the arrival process that we described is poison, then what about the inter-arrival time? That is the time between two packets. Now, the theorem states that if the arrival of packets is governed by Poisson process, then the inter-arrival time between two packets is given by an exponential PDF. So exponential means lambda e to the power minus lambda t. So this is the inter-arrival time probability distribution PT. Lambda e to the power minus lambda t. Okay. So the MM1Q here, MM1Q. So what is another property? This is called the memorylessness property. So MM1Q is memoryless in the sense the amount of time the person in the server has already spent being served is independent of the probability of the remaining service time. So just because someone has spent a particular amount of time, because it is exponentially distributed, exponential distribution is memoryless. That's why this service time is also memoryless. So just because a particular packet has spent say 10-second time in processing does not mean that it will not spend the remaining 5 seconds. It will hurry up and do it within 2 seconds, like that. So the amount of time it has spent, that is not registered in the memory. It will just finish when it has to finish. It will not depend on the memory. So MM1Qs are memoryless. So, and this memorylessness feature is unique to exponential PDFs. This can be proved that a continuous probability distribution is memoryless if and only if it is exponential. You can take it as a homework to prove that inter-arrival time is exponential. So the exponential, if a particular distribution is memoryless, then it has to be exponential, or vice versa. Exponential distribution is the only distribution in continuous domain to be memoryless. Now, having learned the basics of exponential of queuing theory, let's move on to some problems. So utilization factor of a queuing system is, let's download this. So the first question is that the utilization factor of a queuing system is defined as the ratio of the rate at which work enters the system. Ratio at which the work enters the system to the average rate at which the system can perform this work. So utilization factor here is defined as the ratio of the rate at which work enters the system to the average rate at which the system can perform this work. So if we frame it in other words, what is given here is that the rate at which work enters the system. Just follow this definition. The rate at which work enters the system. So the rate at which work enters the system, what do you call it? This is called the arrival rate. And the average rate at which the system can perform work. That is, it can provide service. What is the rate at which it can provide service? So this is called the service rate. And utilization factor is defined as rho is equal to arrival rate by service rate. So it is kind of indicative of the load that a particular server has. So if one server can service, if a particular server can service one customer per minute and another server can service two customers or two packets per minute, so for the same arrival rate of 10 packets per minute, one has a lower utilization factor of 10 because the arrival rate is 10 packets per minute and the service rate is 1 packet per minute. So he has a utilization ratio of 10, so he will be blocked for the next 10 minutes. Whereas the one who can work faster and has a processing rate of 2 packets or 2 customers per minute, he will only need 5 minutes. So he is getting utilized less as compared to the one who has a processing speed of 1 customer per minute. He is the one who has a higher service rate for the same arrival rate will get utilized less because they are not being used for that long of a time as compared to one with lower service rate. So service rate is higher, then utilization factor is lower, and vice versa. So it is kind of indicative of the load that a particular server faces. So lower service rate means for the same arrival rate you will have to have higher load, because if you are working slow, then of course you will have to work longer hours. If you work fast, then you will have to work comparatively lesser hours. Next, calculate the average queue length of a system if the average customer arrival rate is 5 customers per second and the average system time is 20 seconds. So here they have asked for the average queue length of the system and the customer arrival rate is 5 customers per second and the system time is 20 seconds. Here we will be using Little's law. So before going into that, let us first read what is Little's law. So to understand Little's law, we will first have to understand the basics of queuing theorem in a bit more detail. So here this is the textbook. This is called the Klein-Rock queuing theory. So it is by Klein-Rock and it is called queuing theory. The author is Klein-Rock. So here let us denote NT is the number of customers in the system at time t, and UT is the remaining time required to empty the system of all customers present at time t. So NT is the number of customers in the system. So this system includes the one who is getting serviced and the others who are in queue. So the total of the people in queue and the people getting service. This total this total is NT, and UT is the remaining time required to empty the system of all customers at present at time t. So if the nth packet, here another notation is that the nth packet arrives at time tau n. So tau n is the arrival time, and Tn is the inter-arrival time between the n-1th packet and the nth packet. So Tn is equal to tau n minus tau n minus 1. So tau is the timestamp of arrival, and Tn is the duration between two arrivals. And then we have defined various things like waiting time, system time. So what is waiting time and what is service time? So Xn is the service time and Wn is the waiting time. So we have to wait for Wn time. The packet n has to wait for Wn time in queue, and then it will get serviced for Xn time. So Wn plus Xn is the total system time. So system time is the queuing time plus the service time. Now it has some definitions bearing to the derivation of arrival distribution. We will not go there. So here you can see that packet Cn arrives at time tau n, packet Cn plus 1 arrives at tau n plus 1, packet Cn plus 2 arrives at packet time tau n plus 2, and then the inter-arrival time is Tn plus 1, and here the inter-arrival time is Tn plus 2. And then the Cn packet which is coming at time tau n here, as the time progresses, this is the time axis. So as the time progresses, it is waiting in the queue, finally its number comes here. So it gets processed here, and once it gets processed, then here you can see here the packet coming out is Cn minus 1, not Cn, because the Cn just went to the server. That means Cn minus 1, the packet just before Cn, has finally finished servicing and it will get out of the queue system. So when Cn arrives at the servicer or server, the Cn minus 1 packet will exit the server. Similarly, when Cn plus 1 packet, the packet that arrived here, finally goes to service, that is the time when Cn packet has finished servicing. So in point of view of the Cn packet, what time did it spend from the point of view of the packet Cn? What time did it spend? First it spent the time Wn, which is from here in the queue to here. So this time is Wn, this time to this time. This is the Wn time. So here it waited in the queue, the packet Cn waited in the queue. And in Xn time is the time the packet needed to get serviced. And then once Cn exits the system, then Cn plus 1 packet which has arrived here will finally go to service, and Cn plus 1 packet will finish servicing after some time. But no new packet has come, so the queue is currently empty. And then Cn plus 2 packet comes, and whenever Cn plus 2 packet comes, as queue is empty, immediately it goes to service. So here Wn plus 2 is 0, the waiting time is 0, and then it will get serviced for a time Xn plus 2 and finally exit the system. So these all Xn's, the service times, and all the Tn's, the inter-arrival times, are different, but they are exponentially distributed. They are random, but they are exponentially distributed. Now, to derive Little's theorem, what we will do is we will define alpha t as the number of arrivals in duration time 0 to t. So alpha t is the number of packets that have arrived in the time duration from 0 to t. And delta t is the number of departures in the same time frame. So we are taking a time frame 0 to t, and in that packets are coming. See, here it was 0 packets, then 1 packet came. After some time, second packet came. After some time, third packet came. After a long time, fourth packet came. Then fifth packet, like that. This is the alpha t, or the number of packets that are arriving. And similarly, there is the number of packets that are getting serviced. So that are exiting. They are getting serviced and exiting. So here we see the first packet came here and the first packet exited here. So for the first packet, the service time was this much. This much was the service time for the first packet. Then after the first packet, the second packet leaves the system, then the third packet. So the difference, what is the difference? The difference is the number of packets that are in the system, that are in queue plus server. So the packets in the queue plus the packets in the server. So all the packets in the system, queue plus server. This packet is this number of packets is the difference between alpha t and delta t. This difference can be 0 when the packet that just arrived got served. So this difference is 0. Or this difference can be any other value. So this difference is the nt equal to alpha t minus delta t. But it will never be negative, because the number of arrivals will always be greater or equal to the number of departures. A packet cannot depart if it has not arrived, right? This is common sense. So nt is alpha t minus delta t. So this, now what is the arrival rate? Arrival rate is alpha t by t. So the time duration t, if you divide that by that, you will get the arrival rate. And finally, we will define gamma t as the number of packets that have spent some time in the queue. So gamma t is basically the difference between alpha t and delta t. So rather, the number of packets is nt, and on the other hand, the total area between these two curves up to some point represents the total time all customers have spent in the system. So during the interval, let us denote this cumulative area by gamma t. So gamma t is the time that that all the customers have spent in the system. So this is cumulative. So if in 3 seconds, time, 2 customers have waited and one customer has got serviced. So 3 plus 3 plus 3, there will be 9 customers. That there will be 9 seconds of total system time. So you try to understand this in a 3-second interval. So small t is 3. In a 3-second interval, there are in a 3-second interval. So let us write this first. So in a 3-second interval, t equal to 3. Three-second interval, 2 packets have waited completely. So these 2 packets have completely waited. 1 packet arrived at t equal to 1. 1 packet finished service. So one packet finish service at t equal to 2. So one packet will begin service at t equal to 2. So this one has experienced service from t equal to 0 to t equal to 2, and this one has experienced service from t equal to 2 to t equal to 3. So what is alpha t? Number of arrivals. Number of arrivals is one packet was two packets here, third packet here, fourth packet here, and fifth packet here. So number of arrivals is 5 packets. 5 packets are total. And number of departures, just one packet exited service. So delta t equal to 1. And NT, that is the number of packets still in the system. How many? 5 minus 1, alpha t minus delta t. So 5 minus 1, 4. There are 4 packets in the system. So there are 4 packets in the system. Now, what is gamma t? Gamma t is basically the number of customers, the total system time of the customers. Gamma t is total system time of all customers. So individually we will So what is the system time of the first 2 packets? They have waited completely. So 3 plus 3. They have all waited, both waited 3 seconds. One packet arrived at t equal to 1. So it has waited from t equal to 1 to t equal to 3. So it has 2 seconds waiting time. One packet finished service at t equal to 2. So it has 0 waiting time, but it has a service time of 2 seconds. And one packet began service at t equal to 2. So it was waiting for 2 seconds, and then it began service. So 2 seconds of waiting and 1 second of service. So total gamma t will be seconds. So 6, 8, 10, 13 seconds. So gamma t is 13 seconds. Now, what is the what is the average system time? So the total system time of all the customers is 13 seconds. And what are the number of customers? The number of customers is 4. So average system time capital TT is equal to gamma t by nt. So gamma t by nt here is 13 by 4. 3.125. Sorry, 3.25. And now what is another, we have to get another definition, that is we have to get another definition, that is the average customers in system or average packets in the system. So what is the average system time and average, what is the average number of packets in the system? So at a particular time, if you look into it, what is the expected number of packets in the system? So this will be given by NT by T. So this will be, in our case, this will be sorry, not NT by T, rather gamma T by T. So gamma T is the number of customers times the number of gamma T is basically the product of number of customers and the time they have spent. So it is the accumulated time sum. So if you divide it by the time, you will get the average number of customers in the system or average number of packets in the system. So this will be 13 by 3. So which is 4.33. So at a particular time, there on average there are 4.33 packets. Now we see that this gamma T, this one will not be gamma T by NT, since 5 packets have arrived, so it will be gamma T by alpha T, the number of packets that have arrived. So it will be 13 by 5. Now this leads us to Little's theorem. As you can see, this is gamma T by alpha T and this is gamma T by T. So if we divide these two, let us denote this by NT. So if we divide these two, like nu T by capital T of T, if we divide these two, what we will get is gamma T by T by gamma T by alpha T. So this is alpha T by T. These two will cancel, the gamma T's will cancel. So this will be alpha T by T. Now what is alpha T by T? This is lambda T, the arrival rate. Here also you can verify that if you do this nu T by Tt, nu T by Tt, you will get 13 by 3 by 13 by 5. So 5 by 3. And what is the arrival rate? 5 packets have arrived in 3 seconds. So the arrival rate is 5 by 3. So nu T is equal to Tt into lambda T. Or this is the famous Little's theorem. So let us highlight this. This is the Little's theorem. Little's theorem, which says average number of packets in system is equal to system time into arrival rate. So now the problem that we had is a straightforward application of Little's theorem. Here you can see the customer arrival rate is 5 customers per second and system time is 20. So what is the queue length, or the number of packets in the system? Number of packets in the system, this is basically the queue length. Number of packets in system is equal to, so this new t will be gt, which is into lambda t, so 20 into 5, so this will be 100. So number of packets will be 100. Correct answer is to be. Now, the Poisson distribution can model a system where two events occur simultaneously. This is outright false. Poisson system cannot model a system where two events occur simultaneously, because one by one the packets will come and one by one the packets will be served. This one by one is the key here. So everything will happen one by one. Two packets cannot arrive at the same time. So this is obviously we cannot model that. So this is not true. Next, the average number of customers arriving at a bank during a 1 hour period is 20. Find the probability that 10 customers will arrive during a 1 hour period. So here the average customer is 20 per hour. So average arrival rate of customers is 20 per hour. Lambda is equal to 20 per hour. Now, probability that n customers arrive in t time. What is this? This is P n t. Now this is exactly governed by the Poisson distribution. So it will be e to the power minus lambda t into lambda t to the power n by n factorial. Now n is 10 and t is 1. So e to the power minus 10 and t is 1 and lambda is 20. So 20 to the power 10 by 10 factorial. E to the power minus 10 into 20 to the power 10 by 10 factorial. E to the power minus 10. Sorry, e to the power minus 20, because lambda is 20, not 10. E to the power minus 20 into 20 to the power 10 by 10 factorial. So answer is B. So here e to the power minus lambda t, where lambda will be the average, so 20, and n will be the number of packets that will arrive in the particular time t. Now, the same lambda is in this question also. This is a continued question. Here, the mean number of customers arriving at a bank during a 1 hour period is 20. So lambda is equal to 20. Now, lambda is equal to 20 per hour. So here t is, but here t, the time, is taken to be 2 hours. So what is the probability that 10 customers will arrive? So here we have to find P 10 2. So here P t is 2 and n is 10. So e to the power minus lambda t. So e to the power minus lambda t to the power n by n factorial. So here n is 10 and lambda is 20 as usual, and t is 2. So e to the power minus 20 into 2, 20 into 2 to the power 10 by 10 factorial. So here we will have e to the power minus 40 into 40 to the power 10 by 10 factorial. E to the power minus 40, 40 to the power 10 by 10 factorial. Correct answer is option A. Now, traffic intensities are denoted by, so this is general knowledge question. So traffic intensity, what is the unit of traffic intensity? It is R lengths. The unit is R lengths after Danish scientist named Erlang. So this is just general knowledge question, nothing to explain here. Next, if x and y are two independent Poisson random variables with lambda and mu mean respectively. So x and y are two independent arrival processes. So one arrives with a mean of lambda, so e to the power minus lambda t to the power n by n factorial, and another is e to the power minus mu t. So x is distributed as e to the power minus lambda t to the power n by n factorial, whereas y is distributed as so find the distribution of x plus y. This is a very interesting question. The answer is lambda plus mu. So if anyone is there in this meeting, I will request them to please try this. Take 5-7 minutes and try this. Because if you can solve this, then your Poisson system concepts are clear. So try this. So now it's 7 o'clock. At around 7:05, 7:07, I will come and check if anyone is there and has solved it. If not, then I will solve it. So let's take a 5 minutes. So, okay, sorry, not this one. Yeah. So we move to the proof of So we move on to the proof for this Poisson distribution problem. So z is given to be x plus y. Now, so what is the probability that the x plus y is a particular number? So we need to find the probability density of z. So usually when we want to find probability density of a particular random variable, we evaluate the expression px plus y is equal to k, pz is equal to k. So let so here px plus y is equal to p of x plus y is equal to k. So what is the probability that a particular value of x plus y is realized? So x plus y is equal to k in this case. So what is that probability? So that probability will be the summation of all the I equal to 0 to n probability that x is equal to I, and if x is equal to I, y is equal to n minus I. So sorry, not n, k. So here the total is k. So x plus y, the total is k. So if x is equal to I, then y will be k minus I. So I can be 0, then x equal to 0, y equal to k. Or I can be 1, then x equal to 1, k equal to y equal to k minus 1. Like that, finally I can be equal to k. Then x is equal to k and y is equal to 0. So in this case, this is p x equal to I, y equal to k minus I. We have to find the probability distribution of this. Now, x and y are independent processes. So the value of x does not, the value of the x does not depend on the value of y. They are two independent processes. So of course we can split them. So for two independent processes, the intersection is equal to the product of the probabilities. So we know this. So p x equal to I, p y equal to k minus I. Now, since they are distributed by Poisson, we just put the values of the Poisson distribution. So since x and y are Poisson, we just put e to the power x is distributed as lambda. So e to the power minus lambda, e to the power minus lambda I into lambda I, sorry, e to the power minus into e to the power minus lambda t, lambda t to the power I packets by I factorial, and another will be distributed as mu. So e to the power minus mu t to the power k minus I by k minus I whole factorial. Now this will be equal to e to the power minus lambda plus mu t by I factorial k minus I factorial now. What we will do is we will divide on both sides by k factorial and we will take out the k factorial. So this is basically e to the power minus lambda plus mu into k factorial 1 by k factorial. We will take this out. So summation I is equal to 0 to k factorial by I factorial into k minus I factorial into lambda t to the power I mu t to the power k minus I. Now this is basically the binomial expansion of x plus y to the power n. So this is basically the binomial expansion of x plus y to the power n. So this is binomial expansion. So it will basically become e to the power minus lambda, e to the power minus lambda plus mu whole t whole into t by k factorial into lambda t plus mu t. So lambda plus mu whole t basically. Lambda plus mu whole t to the power k. So this will be basically Poisson with parameter lambda plus mu. So it is again Poisson, the sum of two Poisson distributions. So this will be Poisson and the sum of two Poisson distributions is Poisson with the parameter lambda plus mu. So the correct answer is option A. Now question 8. At a bus stop, the buses arrive at an average interval of 30 minutes. At bus stop, the buses arrive at an average interval of 30 minutes. If assume that the bus arrivals are modeled by Poisson process. If a passenger arrives at random, the waiting time for the passenger is. So basically, you have to find the average waiting time of a Poisson queue. So the buses arrive at the inter-arrival time lambda is equal to 30 minutes, and if you come, so what is the average waiting time? So the time length between it follows. So inter-arrival time is 30 minutes. So if the inter-arrival time is 30 minutes, so at every 30 minutes the buses will arrive, and since this this inter-arrival time is 30 minutes and it is distributed in an exponential distribution, inter-arrival time is equal to 30 minutes. So as inter-arrival time is distributed exponentially, as interval time is distributed exponentially, the interval distribution is memoryless. So as the interval time is distributed exponentially, so the distribution is memoryless. So waiting time, irrespective of how many people have come and how many buses have come before, waiting time will always be equal to 30 minutes. So the average waiting time is always 30 minutes. Now, a fisherman who catches fish according to Poisson distribution with lambda equal to 0.5 fish per hour. So he catches half a fish an hour, that is to say one fish per 2 hours. So the fisherman always fishes for at least 2 hours. That is, he always catches one fish. If during these 2 hours he catches at least one fish, he goes back home. Else he keeps fishing until he catches his first fish and then he immediately leaves. So here Poisson distribution with lambda equal to 0.5 fish per hour. The fisherman always fishes for at least 2 hours. If during these 2 hours he catches at least one fish, he goes back home. Else he keeps fishing until he catches his first fish and then immediately leaves. So he will leave if the waiting time is more than 1 hour, to more than if the time is spent is more than 2 hours and he catches one fish, or if the time is more than 1 hour, 2 hours. So if the number of fishes caught in 2 hours is 0, then only he waits for the extra time. So there are two possibilities, that he catches one, he catches at least one fish, or he catches no fish. Then he catches at least one fish or he catches no fish. So these two are complementary ones. So if he catches no fish, then he waits for the extra time. So first we will take the first case, case 1. Fisherman catches at least one fish. So what is the probability of that? Then he will wait for, so what is the expected number of, else he keeps fishing. So what is the expected number of caught fishes? So if he catches at least one fish, then of course, if he catches at least one fish, then of course he will not wait beyond 2 hours. So basically the average number of fishes caught in 2 hours. So in this case, waiting now, here basically we have to get the expected number of fishes. So in this case, if he catches at least one fish within 2 hours, then basically the problem turns to how many fishes does he catch in 2 hours. So average number of, if he catches at least one fish, then the expected number of fish will be equal to the number of fishes caught in 2 hours. So expectation is equal to the expectation of the Poisson process. So expectation of y x into lambda e to the power minus lambda by lambda to the power x e to the power minus lambda by x factorial. So here this is basically, we know this will turn out to be lambda. So in this case this is 1. So if he catches at least one fish, he is expected to catch one fish. But there is another case. So we will take this case downstairs here. So case 2. Fisherman catches no fish in 2 hours. Then basically he will only catch one fish. So what is the probability of that happening? The probability of then he will fish for some more time, and finally when he catches one fish he will leave. So the expectation of this happening, this event y happening is 1. So because he will catch only one fish, so 1 into probability of this happening. So what is the probability? The probability is simply px equal to 0. So 1 into lambda to the power 0 e to the power minus 1 lambda t e to the power minus lambda by 0 factorial. So lambda to the power 0 is 1, 0 factorial is 1, so e to the power minus lambda, so e to the power minus 1. So the total expectation is, so therefore total expectation will be 1 plus E inverse. So this is 1.3679. So 1 plus E inverse or 1.3679 is the correct answer. Now the last question is, a corporation gets on average 500 emails in each 8 hours of work. What is the probability that in 10 minutes the corporation will get at least 2 emails? So lambda is equal to 500 emails per hour. So 500 emails per 8 hour. Sorry, 500 emails per 8 hour. So what is the per minute rate? So 500 by 8 into 60. So the per hour rate is 50 by 48 per minute. Now 50 by 48 per minute or 25 by 24 per minute. So 25 by 24 per minute means some 25 by 24, let us do is 1.04. So there are 1.04 emails per minute. Now the class is from 6 to 8. The class is mostly over now, so we are discussing the last problem. Anyways, so the lambda is 1.04 per minute. Now the probability that it will get 2 emails, the corporation will get 2 emails. So to the probability, this will basically become, we have to learn that the probability that we will get n packets in time t is given by e to the power minus lambda t to the power n by n factorial. Now here we have to find the probability that we get 2 packets in 10 minutes. So 1.04 is the rate, so e to the power minus 1.04 into 10 by 1.04 into 10 whole to the power n. N is 2 packets by 2 factorial. Is it exactly 2 packets or at least 2 packets? Sorry, at least 2 events. Sorry, so this will not be P210. This will not be P210. It is at least 2 events. So at least 2 events means basically your condition will get violated if you don't get any email or you get one email. So it is the complement of P1 and P0. So this is P is equal to 1 minus P010 and P110. These are the 2 events that should not happen. So 1 minus P010. So e to the power minus 10.4, 1.04 into 10 lambda t. So 10.4 to the power 0 by 0 factorial. So, and this one will be e to the power minus 10.4, 10.4 to the power 1 by 1 factorial. So this will basically be 1 minus e to the power. So this will be 1 minus e to the power minus 10.4 to the power 0 and 0 factorial are all 1. And the next one will be 1 minus e to the power minus e to the power minus 10.4 into 10.4 by 1 factorial. So 1 factorial is 1. So minus 10.4 e to the power minus 10.4. So final answer is 1 minus 11.4 e to the power minus 10.4. So put that in the calculator and you will get 11.4 into e to the power. This one will be 0.0003. So if you subtract 1, so you get 0.9996. So the correct answer is 0.9996. So 99.96%. 0.9996. So correct option is option C. So the correct option will be 9.99658 or 99.96%. There is a 99.96% chance that the company will get at least 10 emails. With this, we will be concluding today's class. So today we did queuing theory, the basics of queuing theory, and we learned about Poisson processes and arrival time, inter-arrival time, and how inter-arrival time is exponentially distributed, and it is memoryless, and or the basic notations of queuing theory. So with that, I will like to end the class. Tomorrow, next week, we will have a class again at next Tuesday, 6 p.m. to 8 p.m. Thank you.